Um, right. Hello, everybody. As you can see, this work is done in collaboration with Jeremy Goodman of Princeton University. Okay. I will be talking, well, not very much about MRI, but there will be something related to MRI in this talk. Let's see. Hmm? Oh, it's a different one. Okay, thank you. All right, okay. So how does usual magnetorotational instability work inside of the disk? The basic mechanism is the transport of MRI is the transport of angular momentum by the magnetic field connecting, say, these two blobs of plasma inside of the disk. However, this is not the only way that magnetic field can transport angular momentum between two different parts of the disk. In particular, if you look, if you think outside of this box, we'll see that it is also possible to transport angular momentum by magnetic loops like this that stick above the thin accretion disk. They're still connecting two fluid elements in the disk where most of the inertia is, but the actual magnetic link is in what we call the corona above the disk. And this is what we call coronal MRI. Let's see. Now, one thing I would like to take a moment to make a little detour to repeat the statement that I made earlier today is once we go into this region, in the low density region called the corona, many of the assumptions that are made within the disk no longer apply. And some of the equations that we are solving, in principle, should be different. However, this is just a sort of remark. I'm not going to go too much into that in my talk. Now, an interesting question that arises is we still have MRI within this disk, regular MRI, and in principle we can have these sort of larger coronal loops also transporting angular momentum. And the interesting question is, which of these two mechanisms is the dominant angular momentum transport process? In particular, how do we go about estimating this? We can estimate the stress, the magnetic stress, say through a certain radius integrated in height through the disk separately and through the corona. It basically boils down to the square of the magnetic field, say in the disk, times the disk scale height. And in the corona, similarly, it's basically the coronal magnetic field times the magnetic scale height in the corona. So the point here is that whereas the gas is concentrated in the midplane due to gravitational stratification, the magnetic field doesn't have to be. It's not subject directly to magnetic forces. So in principle, magnetic fields can extend to much higher distance above the disk. Therefore, what matters is not really the gas scale height, but the magnetic scale height. Well, because we are talking about magnetic angular momentum transport here. The ratio of these two torques is basically can be split for illustrative purposes, can be split into two products. One is the ratio of magnetic field strength in the corona and in the disk, and the other one is the ratio of scale heights, characteristic scale heights. And one can see that, well, we don't really expect the magnetic field in the corona to be ever larger than the magnetic field in the disk. At best, it could be comparable. And then, in principle, one can have a situation where the coronal angular momentum transport dominates if the magnetic scale height in the corona is much larger than the disk scale height, h. Let's see. So we have these two kind of ingredients that we have to consider. One is the characteristic field strength in the corona relative to that in the disk, and the other one is the scale height. Let me consider them one by one. So first of all, what determines the magnetic field in the corona? Actually, on this question, I will not have much to say, I have to say. I will be waving my hands for the next few slides, and then I'll proceed to the next question. But still, I think it's very interesting to kind of lay out what are the possibilities. If one wants to determine the overall characteristic, field strength at the surface of the disk that goes into the corona, one has to consider the processes that result in flux emergence, that is a buoyant rise of magnetic loops from the disk up into the corona. And then the key question is what is the rate of this flux emergence, and in what form does it take place? What kind of magnetic structures are arising? And at the present, we don't really have any theoretical handle on this, any firm theoretical handle on this issue. However, in principle, a lot of insight can be obtained from numerical simulations, such as three-dimensional simulations of MRI in stratified accretion disks, such as those that have been done by all the people who are all in this room, essentially. And most of these simulations were, done in the 1990s and in early 2000s, but with more computer power and better codes, I think one should continue to do this and improve constantly, because there is still a lot of work to be done here. And in addition to just doing the simulations, it's also important to figure out how to analyze the results of the simulations. That is, we are interested in what one has to understand what are the quantities that we should be looking for if we're interested in the emergence of flux into the corona. Not just magnetic energy density, but some more refined statistical quantities. Now, but we also have to understand, of course, what are the physical processes that control the flux emergence. And I think we can start out by basically thinking about this problem as a balance or competition, really, between different processes that result in disruption of channel flows in the following way. If one starts with a linear MRI mode, such as this, it has been shown by Goodman and Xu in '94 that the MRI mode is an actual exact nonlinear solution. So they can grow essentially indefinitely until something else arises that disrupts them, these channel flows. And there is a number of things that potentially could disrupt channel flows. And I'll mention three, basically. The first one is the parasitic instabilities that were actually introduced and analyzed by Goodman and Xu. And I don't know how they look like. Maybe Jeremy does. So I just drew something like this, because the idea is that they lead to development of three-dimensional turbulence. And they basically destroy these coherent magnetic structures and result in turbulent cascade that dissipates the energy locally within the disk. In principle, another form of secondary instability, in the case when the resistivity is relatively large, and so it's still, say, the global Lindquist number is still larger than 1, but maybe not very large, in principle could be, let's see, tearing mode. In principle, this channel flow is it's essentially a current layer, which can be subject to tearing mode, in which case there will be these magnetic islands produced. And as far as I know, this hasn't been analyzed, hasn't been studied in any detail. And I think it's, I just would like to encourage studies of this, because I think tearing mode is known to have a very interesting behavior, both linearly and non-linearly. And I think something useful can be done here. But from the point of view of my main interest, that is the accretion disk corona, the important secondary instability that feeds off of the primary MRI mode is the Parker instability that leads to buoyant rise of some part of the magnetic field line and presumably this goes out from the disk into the corona and forms these coronal loops. Okay, so now let me turn to the second question of what determines the magnetic scale height in the disk. Sorry, in the corona. So we are imagining a situation where there is a bunch of magnetic field lines that connect 2 points on the disk, and they all have different sizes and orientations and evolve all the time. And we want to figure out what is the characteristic size of these things. But to do this, we probably ought to ask more general questions. For example, not just what is the magnetic scale height, but what is the distribution of magnetic energy density with the height above the disk, because it's some function. Specifically, we're interested in the range of scales much larger than the gas scale height of the disk, but still much smaller than the radius. If this function has a characteristic scale, which I call h sub b, then what is this scale? What determines it? How large is it compared with h and with r? And if it doesn't have a characteristic scale, if it's a power law, then what is the power law exponent? One can also ask what is the distribution of dissipation with height. That's more relevant to actually to observable quantities, to producing non-thermal radiation and so forth. And then on top of all of that, or kind of more at an even more fundamental level, one would like to ask, what is the distribution of magnetic structures in this corona? Once we have some answers to all of these questions, we could then address the question of what is the role of this coronal magnetic field in the overall angular momentum transport. And since the title of my talk mentions the word reconnection, and as I will show in my talk, all these things directly depend on the efficiency of magnetic reconnection in the corona. Now, so to develop this kind of theory, we use the following approach. First of all, one has to recognize that this coronal magnetic field ought to be treated in some statistical way, with some statistical terms. So we are following a program which was actually first pioneered by Taut and Pringle 12 years ago, but kind of we are including more realistic physics, and we also producing more output out of it. That is, we analyze what the results mean. But the basic idea is that we treat the corona, well, first of all, the corona is believed to be force-free, which means that magnetic field dominates the dynamics. And to some extent, what the gas is doing is not important at all. So we don't care about the gas density and temperature. We only care about magnetic structures. We then represent the corona as an ensemble of magnetic loops. And for simplicity, each loop is characterized basically by its length and the orientation with respect to the toroidal direction, or equivalently by the azimuthal and radial foot point separations. Then we introduce the distribution function of these loops in this parameter space. And then we look at the physical processes that we believe are important in this corona to figure out what are the equation of motions of these loops individually and how they interact with each other. And from this, we is it really? But I only started 15 minutes ago. Cheating. Well, okay. Well, anyway, so and then the goal is to derive the equation, the kinetic equation for this loop distribution function, and to obtain a statistical steady-state description of it. I have a bunch too. Right. So the basic physical processes that we think are important here are the following. First of all, it's the way the corona magnetically interacts with the disk on small scales. That is, the primary reason for the existence of the corona is flux emergence. So we have to somehow include the emergence of small loops and submergence of small loops back into the disk that occur on scales comparable with the disk thickness. Within this theory, we cannot address this question. So for us, it's an input that would be obtained from the previous part, from considering the stratified disk. Now, so this would be sort of a source function, if you wish. Then one of the most important physical processes in accretion disks, of course, is Keplerian shear. And this is relatively straightforward. A given loop, if it has foot points at different radii, it will be stretched azimuthally and will grow as a result. And then, in addition to that, in principle, disks are turbulent, so the foot points of these loops will be subject to random walk in the horizontal plane, two-dimensional random walk. And on average, these processes ought to lead to pumping of magnetic energy from the disk into the corona. There is a Poynting flux associated with all of these on average. To get a meaningful steady state, we also ought to have a process that relaxes magnetic energy, that dissipates the magnetic field and relaxes the stresses and brings the field back to closer to the potential state. And this process is reconnection. Within our model, it's reconnection between different loops in the corona. Observationally, these reconnection probably occurs in individual separate events which are observable as flares of various sizes. Another reason why reconnection is important in this particular context is that whereas Keplerian shear alone can create loops that are large in the azimuthal direction with large foot point separations in the toroidal direction, it cannot increase the radial foot point separation, at least non-trivially. So reconnection may be important from the point of view of creating a population of loops that are connecting points on the disk separated by large distances compared with the thickness of the disk. So there is some sort of reconnective inverse cascade, and we want to be able to quantify it somehow. So, but overall, the physical picture of the corona is that some sort of boiling foam of magnetic loops rising from the disk constantly, and then in the corona they sometimes merge with each other, forming larger loops, and this whole thing proceeds on a variety of temporal and spatial scales all the time.
Are you saying you expect an inverse cascade because of the merger? Is that what you said?
It's what one could call, and what actually I think Taut and Pringle called inverse cascade. It's building up a population of loops with large radial foot point separations.
I mean, you can get inverse cascade without merger.
Hmm?
You can get inverse cascade without merger. It's just a sort of.
Well, you have to understand how you would do it in this context. It's not trivial. You will get, because one thing I have to say, we think of this corona as a force-free environment, in which case the usual intuition that people have from studies of MHD turbulence, I think, doesn't apply at all. You're just not in the regime where you could talk about this as a turbulent system. And the main reason for this, I think, is that in turbulence, in MHD turbulence, one thinks perhaps in terms of packets of Alfvén waves, which have longitudinal scales smaller than the size of the system. And in this case, it's not correct. This assumption is not correct. That is, well, I'm not going to get, I can address this if I have time. Don't want to spend time on this right now. Anyway, so the final result is basically writing down a kinetic equation for this loop distribution function, f of a. A stands for loop, a type of loop, that has various terms. And overall, this equation, our goal is to derive an equation that would be similar to Boltzmann's kinetic equation. This equation may have a source term due to flux emergence. Alternatively, flux emergence can be represented in terms of boundary conditions at small scales. It will have a diffusion-like term, which in general is anisotropic, that describes the random foot point motions on the surface of the disk. it will have a relatively trivial Keplerian shear term, which is just advection, with a velocity that is itself proportional to the radial foot point separation. It's driven by shear. And then finally, there is this collision term, which arises from reconnection. And this, of course, is the most non-trivial but very important term. And I'll spend one slide on it. Basically, reconnection acts as a binary collision between particles in a gas. That is, we have two loops that come together, reconnect from two new loops. Under certain approximations, we can derive reconnection rules that tell us what are the parameters of the two daughter loops in terms of the parameters and relative position of the two incoming loops. And then we can write down in some sort of schematical form, at least, this reconnection term as a nonlinear integral operator similar to Boltzmann's collision operator that involves a certain kernel. And this kernel is, this physical meaning is it's a rate of reconnection events between loops of given type, per unit time, per unit surface area of the disk. And this is where our ignorance lies to some extent. It's parametrization. On dimensional grounds, we argue that it ought to be proportional to the shear or the Keplerian rotation rate, and also to cross-section of loops, which has to do with just the geometrical size. And then there is a dimensionless coefficient in front, which we call Q, which is could be regarded as of order unity or perhaps smaller than unity. And this Q describes the efficiency of reconnection. All right, okay. It describes the overall efficiency of reconnection. If Q is small, it means that reconnection is relatively unimportant relative to Keplerian shear. And then we solve this equation numerically, and we obtain distributions, statistical steady-state distributions, corresponding to different values of this reconnection parameter, because our focus is to study the effect of reconnection on this corona. In particular, we see that if say Q is equal to infinity, which means that Keplerian shear is turned off, then the system by itself is totally isotropic. And therefore, the distribution function of loop in sizes is independent of the angle. We always find a power law, and it's just some power law here. Now, if we then...
So is that the solar value?
No. I mean, what knows what solar value is? There is no solar value.
Well, wouldn't you like your theory?
I would like, but...
To
right, but there are... OK. First of all, it wouldn't apply there. Second of all, there is no observational data on the solar value. There is no loop distribution.
No observational data on what?
There is no, at least, published distribution function of loops that I've seen in the solar case.
Yeah.
OK, let me go on then. And I have to say that, I mean, this whole area is in its infancy, in a sense. There is much less known about the force-free stochastic systems such as this, as opposed to turbulence.
Amount of data about the solar corona relative to what we'll ever have about the
About the disks, yes,
so
yes, yes.
Generalize one model and apply
Exactly. I agree, and actually, I think that many of these ideas and tools may be applicable to the solar corona. But there are important differences, and also the magnetic information about the solar corona is limited. People measure magnetic field on the surface of the sun. What happens in the corona is inferred by assuming something about what the equations are, usually. Well, anyway, then the important points, sort of if you make your reconnection relatively inefficient and you increase the shear, then you would expect, of course, that you will have more elongated loops in the toroidal directions as opposed to the radial direction, and your distribution function is anisotropic, and this is indeed what we find. By the way, in this model, we always find that the distribution function in terms of size is always a power law, but the exponent depends on the angle, and it depends on this value of Q. so in this case of Q equals 3%, for example, we find that the purely toroidal loops has a shallower power law, and purely radial loops have a steeper power law, and so forth. So we have at least a way of calculating these things. And then once we know how to calculate the distribution function, we can actually go ahead, and there is a nice, I think, in my view, a way to calculate global energetic quantities and torques once you know the distribution function. And in particular, we find, and this is probably the most important slide here, is that as reconnection becomes more and more inefficient, if you suppress reconnection, then your loops grow to larger height, they become larger, and they grow to larger height. This is because they're stretched azimuthally by Keplerian shear to larger distances before they have a chance to reconnect. So the overall magnetic sort of scale height, if you wish, increases. The overall amount of magnetic energy in the corona also goes up. And so as Q is reduced, it sort of becomes larger and larger. And similarly, the magnetic torque is also increased rapidly. And let's see. OK, I'll just skip this and finish with a summary. The basic point is that magnetic field in the accretion disk corona can contribute, in principle, to overall angular momentum transport, especially if the magnetic scale height is larger than the disk scale height. To quantitatively assess the effect of this coronal magnetic field on the angular momentum transport, one has to analyze both the processes that occur in the disk, such as Parker instability in a stratified disk and so forth, and the processes that occur in the corona itself. And the first issue is that is how much magnetic flux is emerging from the disk I think is basically determined by some competition between different secondary modes that may grow on top of a primary MRI mode, in particular Parker instability versus parasitic instabilities. Once you are in the corona, then one should apply some sort of statistical description to an ensemble of loops that describe the coronal magnetic field. And importantly, as we've shown here, magnetic reconnection controls this distribution function and therefore the magnetic energy density and all the global quantities. I'll stop here and thank you.
Okay, a few minutes for questions. I'll take Eric first.
Actually, a comment on Elliot's thing. I think in the sun, the number density of structures is n of E is e to the -2. And so you could then scale E with L.
Yeah. Well, in the sun, what is the most important and most sort of widely circulated power law and most discussed power law in the solar corona is the number distribution of flares as function of energy. Then how do you go from that to that? It's still a question.
Scales with I think it's not bad to assume it scales with some particle length, probably less than 2, between 1 and 2.
Well, but then your assumption here, so there are all these things that are correlated, and you have to make sure that you, right. Another point of difference between more realistic picture that we would eventually want to develop and the one that we developed here is that here we just treated this Q as a constant, independent of any physical parameters and sort of uniform everywhere. In reality, I think, and in particular in the sun, the efficiency of reconnection depends on the degree of plasma collisionality, therefore on the plasma density, and therefore on the height, how high you are above the disk. And this, I think, would alter this picture. In particular, would introduce a certain scale. In this picture, once you have this just Q, there is no characteristic scale in the system. That's why we are getting power laws.
But if T goes 0, torque doesn't go to 0.
Well, it's the other way around. If Q goes to infinity, I mean, if there is no reconnection, it means that Q goes to 0. If there is no shear, Q goes to infinity.
But you have loop heat, like a monotonic in your torque. It should come back again.
It should, right, it's a good question. The reason for this is that,
Maybe you better explain the question.
oh, okay, okay, right. Thank you, Jeremy. So the issue is that, say, if, actually, let me go to the slide that I skipped. If you have no reconnection, your field is in the corona is essentially potential, in which case its characteristic scale height is similar to the disk thickness, and not much energy is released, not much torque is transmitted. Now, in the opposite limit, when Q goes to 0, which in our language means that you suppress reconnection entirely, you still have shear. The question is, what will the torque be in that case? In the picture that I showed in our model, it just grew monotonically as Q went to 0. This is an artifact of the fact that we are limiting ourselves to essentially kind of a shearing sheet picture where we're considering a small patch on the disk. We are neglecting toroidal effects. We are still thinking about all of these scales as being much smaller than the radius of the disk. However, in reality, once you start considering loops that are as large as the radius of the disk, then the geometry of the expansion changes. And in particular, what will happen in that case is that if the field opens up, if you don't have reconnection, your field being stretched by azimuthal shear will have to open up eventually. And in the non-Cartesian but axisymmetric geometry, when this happens, the torque actually goes down. So it would start going down as soon as your kind of height of your structures starts exceeding the radius of the disk. It would generally.
Okay.
All right, yes.
One question that's quick.
Okay. You'd expect there to be a systematic tendency for the foot points to separate in radius if you're transporting angular momentum.
Yes, yes.
And that doesn't seem to be in your...
Right, because that's another thing that we think is important, and it's what motivated the study, is the angular momentum transport, and therefore the effect of coronal magnetic field on the disk. But in this model, it's not yet included. This model is in this sense passive. That is, the back reaction of the magnetic field on the motion of the disk is not explicitly there.
But you still know how those things should separate if you're...
We know, yeah. We calculate the torques. For example, for a given loop, we calculate the torque. How they should separate in response to this torque depends on the surface density, right?
Okay, I think we better continue